Discussing about the inverse trigonometric functions. Well, the fact that we are going to come up with new inverse functions, that implies the existence of a function that has to be one-to-one in order to be invertible. All right? Well, last time we looked at one example for the sine functions, for the sine function in which, well, we find out that the function is not, it can't be inverted. It's not invertible because it's not one-to-one. It fails the horizontal line test. Let's see what happens with the cosine function on the other hand. All right, so y equals to cosine x, and change brush, okay, whose graph looks very similar to that of sine. However, that one cycle looks like this, and you may go ahead and do more cycles to the right, to the left. All right, and again, let's do the horizontal line test and see how the horizontal line in this case fails to cross at most once, right? So it crosses more than once, so that's why this function is potentially not invertible. And even though we skipped this section about tangents and what and the like, y equals to tangent, whose graph looks like this. Well, sort of like this. With what else? It has these vertical asymptotes. And if we do the horizontal line test again, it fails. So with this, then we are essentially screwed about trying to find inverse trigonometric functions. So because they're not one-to-one, they all fail the horizontal line test. However, last time I mentioned that there is like a trick, if you will, so we can come up with invertible functions. And the trick here, check this out. The trick is to restrict the domain to some window where the horizontal line doesn't cross more than once. For example, well, we know that the domain of the y of the sine function is all real numbers, and the range goes between -1 and 1. And likewise for the cosine function, the domain is all real numbers, and the range also -1 to 1. All right. And well, the tangent function, the domain, well, it's not all real numbers. In this case, the domain, it's actually, okay, let me write it down in words. Odd multiples of pi over 2. Like in this case, this is a vertical asymptote, or except the domain excludes, exclude odd multiples of pi over 2, because this is the asymptote at pi over 2, negative pi over 2, 3 pi over 2 is another vertical asymptote, 5 pi over 2, same on the left, into the left direction, negative 3 pi over 2, negative 5 pi over 2. Right? So those are the restricted values for the tangent function. And the range, it's in this case all real numbers, because if we see this graph right here, they extend from the very bottom to the very top. So that indicates that the range is going to be all real numbers. All right, well, what's the trick anyway? So the trick here is, so check this out. I'm going to highlight the portion of the graph of the sine function in a way that we can get an invertible function. And that portion of the graph, it's actually between negative pi. Between negative pi over 2 to pi over 2. if we restrict the domain of the sine function to only negative pi over 2 to pi over 2, try the horizontal line test again. Do you see how this time is going to pass the horizontal line test? Only within this window in green this time, not for the entire graph. Same thing for the cosine function. How about let me highlight on a window so that the horizontal line gets passed in this case. Well, so horizontal line test is going to go. Do you see how this time the horizontal line just crosses only once on the graph? Only within the window in this case. What's that? That's 0 and pi. And well, for the tangent function, it would be a function if we only restrict the domain to only, to only one of these periods right here, which in this case range between negative pi over 2 and pi over 2. So that's the trick to turn these trigonometric functions, which originally are not one-to-one, therefore not invertible. Well, we make them one-to-one, therefore invertible, by restricting their domains, by just taking like only one sample or only one piece of the graph. In this case, so the domain, it's not anymore negative infinity to positive infinity. It's going to be this time negative pi over 2 to pi over 2. And for the cosine function, it's no longer all real numbers either. So that's going to be between 0 and pi. Okay? What else? For the tangent function, well, it's no longer all the multiples, all the odd multiples of pi over 2, not anymore. So because we're restricting the domain to only this part in green, which in this case it's going to be, oh, by the way, actually it's going to be the same as the domain for the inverse sine, for the sine function rather. Negative pi over 2 to pi over 2. So that's the trick. Well, it's not necessarily a trick. It's rather setting a condition, rather imposing some conditions to the function. Okay, no, you're not one-to-one, therefore you're not invertible. However, if you agree to trim yourself between negative pi over 2 to pi over 2, well then, welcome to the invertible functions world. Otherwise, well, just as is, they are not invertible functions. All right? Well, so again, my drawings may not be perfect, especially if I wanted to draw the graphs of the inverse functions. Well, we would use the key points, and you might remember this from the beginning of the semester, or sort of the beginning of the semester, how we essentially interchange the order pairs for this function to come up with the graphs of their inverse functions. However, doing them by hand, overlapping all this mess I already have, well, it's not going to be very neat. For this reason, I copied and pasted an image from the textbook illustrating all these graphs that we need to have an idea of how they look like, but most importantly, their specifics. Okay, do you notice here how the y equals sine function has a trimmed domain? It's now the negative pi over 2 to pi over 2, the same way we define it over here. Initially, it was all real numbers for the sine and the cosine function. However, only the graph comprised by the window between negative pi over 2 to pi over 2 gives us an invertible function. Same and for the cosine function goes between 0 and pi. So let me highlight that so you can see. So you can see that. So the new domain, so that it's an invertible function, the new domain, so that it's an invertible function, the new domain, so that it's an invertible function. And well, for the tangent function, the range, it's still the same, all real numbers. The range of both the cosine and the sine function remain negative 1 to 1. So that condition we impose to these three essential functions didn't affect the range, only affected the domain, so that we get these invertible functions. All right, so let's see. A little bit of notation. So if we have the function y equals to sine x, right? Well, to denote the inverse function, check this out. To denote an inverse trigonometric function, you might want to look for this -1, sort of an exponent. We need to be careful with this notation because that negative exponent, you may have seen it before, right? I mean, where have we seen it before? You know, when we have something like x to the -1, for example, which is 1 over x, all right? Or what else? Something like e to the -x, an exponential function, that's 1 over e to the positive x, right? However, well, what are we talking about these two examples? These two examples really represent reciprocals, not inverses. So in the case, and it's listed below here, in the case that when we're dealing with inverse trigonometric functions, well, this -1 symbol doesn't represent a reciprocal. It actually represents inverse, so it would be incorrect to say this. This is not correct. All right. Just wanted to mention this because it's a very common pitfall when we're looking. Oh yes, because it looks very natural to have a -1 power. Send it to the numerator with +1 power. No, it's not the case for inverse trig functions, right? What else? More specifics. Well, whenever we have y equals sine inverse of x, that means that sine y equals to x. So what are we going to do this time? So in this section, in comparison with what we have done throughout this chapter about trigonometry, well, we already defined the 6 essential trigonometric functions: sine, cosine, tangent, and the other 3. What do? Find the sine of pi over 3, for example. Cosine of pi over 4. What else? Tangent of 7 pi over 6. So we found this trigonometric function of an angle, and it gave us, and the output was a real number between -1 and 1. Right? However, this time with the inverse functions, this time they're asking us what angle has a sine equal to, boom, certain number. So we're going to go the reverse. Remember how we went between logarithmic form and exponential form because those two functions were inverses to one another? Well, it's a similar thing here with the inverse trigonometric function. So instead of saying, e to the 5 equals to m, for example, they're asking us, this is log base e of m equals to 5. All right? So, but in this case, for angles, instead of evaluating the trigonometric function of an angle, which is another, whatever output is, whatever number is, now they're asking us what angle is having a sine or whatever trig function equal to the value we want to evaluate. And well, again, here's the specifics for the inverse trigonometric functions. Again, one thing to keep in mind is that every time we relate a function with its inverse, so the original function has a domain. Okay, let me label the domain and the range. Whenever we find the inverse function related to that function, everything gets interchanged. So now the domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function. And that's because, well, you can think of this inverse function as recycling function, as functions just going around a loop, so f inverse. All right, if I input something to this f function, the output will be the input of the inverse function, and then if I input something in the inverse function, its output will be the input of the original function. They're just going to go back and forth like recycling. See what I'm saying? So that's the whole idea with trigonometric functions. Sine of pi over 2 is 1. Okay, now the question is, what is the inverse sine of 1? In other words, what angle has a sine equal to 1? Pi over 2. So that's how we're going to go back and forth. But I guess, that sounds like a lot of words. How about we look at some examples about how we compute this? All right. Find the exact values or state that the expression is undefined. Well, so what do we have? The inverse sine, rather, of negative square root of 3 over 2. All right. So let's see what about it. Yeah, that's fine. Okay. In other words, they're asking us for the angle whose sine equals to negative root of 3 over 2. In other words, so let this be, let's call it y. Whatever number, all right? Okay, what I'm going to do here is the following. This statement implies the following. This implies that sine y equals to negative root of 3 over 2. Okay? And well, of course, back in the previous few sections, we learned about the unit circle. And we know that at least there's two locations in the unit circle or in the Cartesian plane for which the sine is a negative root of 3 over 2. Or we can also think of infinitely many possibilities. And that's because these angles, they just repeat themselves after a period of 2 pi. So if you are at a location where sine equals to negative root of 3 over 2, well, at 2 pi, do a whole rotation, you're going to fall in the same point again. A second rotation, same point again. A third rotation, and so on and so forth, whether you do it counterclockwise or clockwise rather, in the negative direction. However, well, that's what we looked back when we learned this for the first time. However, we cannot just state, oh, negative root of 3 over 2, that's the answer. Well, or whatever angle we can think of. So, number one. So, we look for an angle in the interval negative pi over 2 to pi over 2 such that what's that? Sine y equals, for an angle y, let's call it angle y because yes, notation, right? Negative root of 3 over 2. Well, negative root of 3 over 2, and that's also negative. Well, so how about we do a Cartesian plane? Of course, it will be a lot helpful to have one of those. And well, one thing to keep in mind, remember all students take calculus. How about we label that ASTC? And well, in this case, one thing to look for, one thing to notice is that we're looking for sine to be a negative value. So there's two quadrants where the sine function is negative. What are those two quadrants? Third and fourth. So it could be here, where the y value, which is sine negative root of 3 over 2, or it could be here, where also the y value is negative root of 3 over 2. That's 1/2 and 1/2. All right. However, I claim that there's only one of these two is the correct answer. Which one is the correct answer? Do you have an idea which one is it? The one in the fourth quadrant, right? Because, okay, you might argue, well, maybe none of them, because what's this? I believe this is 5 pi over 3. Is that correct? and this is 4 pi over 3. Is that correct? Okay, so you might argue about, well, neither 4 pi over 3 nor 5 pi over 3 are within the range or within the window negative pi over 2 to pi over 2, right? However, well, as we mentioned before, these angles are, periodic, and we can express, for example, this angle 5 pi over 3 in terms of another coterminal angle, rather with a negative symbol. That is negative pi over 3. All right? And that negative pi over 3 is for sure contained within the window negative pi over 2 to pi over 2. All right? So final answer here. Let me highlight it. Oops. So sine inverse of negative root of 3 over 2. That's equal to negative pi over 3. I know maybe I'm looking at too many details. Maybe we can just look at the unit circle and choose the correct value. Question?
Oh, wait, how do you get negative pi over 3?
Oh, because, well, if we fourth quadrant means 5 pi over 3, right? The angle that contains this order pair on the unit circle. However, check this out. 5 pi over 3, it's not an angle contained within the window negative pi over 2 to pi over 2, right? So we need to represent this 5 pi over 3 as a coterminal angle in a way that the new label, the new angle, which is in the same location, it's a number between negative pi over 2 and pi over 2, right? Which is in this case the negative pi over 3, right? We could have also said maybe negative 7 pi over 3. That's another way to express the same angle. But again, this angle will be incorrect because it's not within this window. Another way to represent this angle is, 5 plus 6, is that 11? Pi over 3 maybe? But do you see how big this angle is? That it's really outside this range. So there's infinitely many ways to represent this angle, but we use the representation that fits within this window. All right? Does that make sense? Let's do more examples about it. So, and well, that's actually what I meant. I mean, there are infinitely many values for x for which sine x equals negative root of 3 over 2, such as 4 pi over 3. 5 pi over 3, negative pi over 3, negative 2 pi over 3, infinitely many multiples or 2 pi multiples of those angles. However, because we needed to restrict this special group of functions so they fit in the world of the invertible functions, we needed to restrict their domains so that we can find their inverse. And that restricted domain, check how it is. Again, just to keep checking the consistency of it. It's negative pi over 2 to pi over 2. So it's not just any angle fits that window. All right? Let's look at another example. What about arc sine of 1/2? In other words, okay, so this is essentially equals to some value y. All right? Okay. This means, by inverse function definition, means sine y equals to 1/2. Well, how about we look at the unit circle to find out what is that value? And well, number one, this time we're looking for the inverse sine. Well, again, it's inverse sine. Inverse sine again. Inverse sine of 1/2. However, notice the sign. All students take calculus. Well, which quadrants have the sine function to be positive? First one, which one, and what other? First and second, right? So we're looking for the order pair that contains the sine value of 1/2, and the order pair that contains the sine value of 1/2 also. For the first point, root of 3 over 2. and negative root of 3 over 2. What are those angles, by the way? I believe this is 60-degree angle and 150, which is in this case pi over 6, and 5 pi over 6. Do we agree with this? Okay, however, what is the restricted domain of the sine function in order to find its inverse? Isn't it trimmed between negative pi over 2 to pi over 2? So that being said, this 5 pi over 6 it's out of the game. And the only angle that fits within this window is a pi over 6. All right? So arcsine of 1/2 equals pi over 6. And again, in words, we look for an angle y within negative pi over 2 and pi over 2 such that its sine function equals to 1/2. And that angle happens to be pi over 6. All right? So far so good? You guys following me up to this point? I mean, later on, after practice and for practical purpose, you will just look at your unit circle. Oh, you're asked to evaluate an inverse sine. Okay, that's the y value that contains this number. So, oh, it corresponds to this angle. As easy as that. But in the meantime, it's important to see what's the concept behind and the connection with the unit circle, the spatial angles, etc. All right. Let us see. Sine inverse of 2. What about it? Well, number 1. So, this is equal to some number y, whatever that is. Okay? And well, so this means, by inverse functions definition, this means sine y equals to 2. So the question is, what angle has a sine equal to 2? None of them? There's no angles? Yeah, you guys are right. Just those of you who are saying no, it's true. This is unfortunately undefined. And the reason to this is because the range of the sine function goes between -1 and 1, all right? And well, what about these two? That number 2, it's outside of the range between -1 and 1. Don't get me wrong, those of you who are engineering majors or even math majors, when you go to complex analysis or functions of complex variables, you will find out that there's actually values of y for which the sine function equals to 2, but hold on, I don't see any intersection points. Do you see intersection points? However, complex analysis which is one of the most wonderful subjects ever, well, it will show you those pretty cool results. So, well, wait until you get to those courses. In the meantime, let's just call it a day and say it's undefined. And that since the range of the sine function is -1 to 1, and of course we can see that the number 2 it's outside of that window. All right? Let's look at another example because why not? All right. Cosine inverse of -1/2. Well, again, let's start with the fact that whatever this madness is, it will be some number y, all right? Or x, your favorite letter, doesn't matter. It's all ultimately it's just a dummy variable. So, And again, by definition of inverse functions, this means cosine y equals negative 1/2. Again, what I'm doing here, it's analogous to what we did back when we work with exponentials and logarithms. We have the exponential version equivalent and its equivalent logarithmic expression, and or vice versa, right? So let's see. This time we're looking for an angle y such that cosine y equals negative 1/2. Now, this time we're looking for cosine, and two things we need to take into consideration: the fact that it's a cosine function and the fact that this is a negative value. That matters, all right? So that's going to make a whole difference. It's going to change the whole game here. Well, again, all students take calculus, and well, we're looking for the two quadrants where the cosine function is negative. What are those quadrants? 2 and 3. Yep, 2 and 3. So that's a point right here, and that's a point right there. All right. So we're looking for the angle whose x-coordinate is negative 1/2. Well, the y-coordinate is root of 3/2. Also negative 1/2 root of 3, or negative root of 3/2 in this case. What are those angles? Well, we can after a few exercises, we can already see some pattern, and we can see how we can actually already ditch one of the angles, right? Because it's out of the range. How about the one in the third quadrant? And that's because the inverse cosine function. And let me go up. Let me go back to the correct window for the cosine function. It's only valid between 0 and pi. That means quadrant 1 and quadrant 2. So whatever other angle we have, just get it out of the way. All right, negative 1/2 for cosine and y, or for x and y equals root of 3. I believe this is that 5 pi over 6? No, it's not 5 pi over 6. I believe it's 2 pi over 3, right? 2 pi over 3. It's always good to double check with the unit circle. Well, I don't have the unit circle with me. Sometimes I mess this once up, but I mean, it's fine. Okay, this means arc cos. Notice I'm using different notation. The cosine inverse can also be represented as arc cos, arc symbol, and that's a 2 pi over 3. Now the question is 2 pi over 3 an angle in between 0 and pi? Well, from the picture, I guess it's clear that it is, right? But I mean, sometimes when we're just looking at inequalities, well, it's a little bit hard to see. That's why the best advice I could give you is draw a picture, draw your Cartesian plane, locate those angles, check in within the specifics for each inverse trigonometric function, and based on that, well, from there you can already tell, oh, it's only this angle right here, or maybe the other one. So that's one way to get through this. All right, inverse tangent of root of 3. Let's see, what about it? Oh yes, I had them here. Okay, so in this case, again, by inverse function definition, well, first of all, this will be some number y. And by inverse function definition, or relation, if we will, this means tangent of y equals to root of 3. Okay? This one, I'm not going to lie, but it's going to be a little tricky. This one is going to be a little tricky, but I'll show you why in a minute. Okay. First of all, again, in words, looking for an angle y such that tangent y equals root of 3 over 1. Now check this out. So do we agree that this root of 3 okay, before getting into the trick. So again, when we're using the unit circle, it's very straightforward for us to check for sines and cosines because again, the x-coordinate of all the units on the unit of all the points on the unit circle, it's representing the cosine function, while the y-coordinate of the points represent the y function. And starts get a little tricky when we get to tangents, secants, tangents, cotangents, secants, and cosecant. Maybe not the secants and cosecants because those are only reciprocals, right? So it's no big deal. However, the tangents are usually a big deal. How about, but the trick for this, how about root of 3 over 1? And I believe I did this trick before. So, and you might want to use this trick as well. Okay? Do we agree that root of 3 is the same as root of 3 over 1? Well, do we also agree, hopefully, that this is the simplified version of root of 3 over 2 over 1/2? Do we agree with this? Because essentially, if we do this backwards in a way, cancel, we get root of 3 over 1, which is the original root of 3. Are you guys following me here? Okay. Because the reason why I'm going even in slow motion for this is because these tricks are usually tricky to do. Okay, now check this out. Let's group. Group the fraction in the numerator, group the fraction in the denominator, and well, let's go back to the very roots of unit circle, points on the unit circle, or the circle of any radii. Do we agree that the numerator, or by definition of tangent, isn't that the y over x? Right? So now we're looking for an angle that has a y of root of 3 over 2 and an x of 1/2. There's actually 2 points, right? What are those 2 points? Oh, come on. Need to use a different color here. Well, number 1, this tangent function is a positive value. So which quadrants have a positive tangent function? 1 1/3, right? Right here, right there. Okay, so this is going to give us the order pair. So that is x equals to 1/2. Actually, negative 1/2. Let me make it neater. Negative root of 3 over 2. And what about negative, positive actually, 1/2 root of 3 over 2. Now, going with the unit circle, what angles are those? Well, actually, I don't think at this point we need to check for both angles. We can already disregard this one, right? Because that's not within the range of the inverse tan function. So the inverse tan function is only defined in quadrants 1 and 4. Well, what angle is this? Start by pi over 3? Pi over 3. So that being said, let me use the other notation so we can get familiar with both notations. Arctan, which is the same as tan inverse of root of 3, equals to pi over 3. And now, is pi over 3 an angle in between? An angle between, I forgot that part, between negative pi over 2 and pi over 2. And yes, indeed, from the picture, we can tell that pi over 3 is an angle within negative pi over 2 and pi over 2. All right? I know this one was a little tricky. Tangents and cotangents get a little tricky. We need to think a little backwards in a way, like what we did here. Yeah, all right. So let's see. What about letter F? Arctangent of -1. Let's do another arctan. All right. Arctangent, that's number 1. Okay. Again, in the end, the result will be just another number, any number, call it y. By inverse function definitions, this means tangent y equals to -1. All right? I wonder how can we get that -1. But first of all, in words, looking for an angle y between, or within rather, the window -π/2 and π/2, such that its tangent equals to -1. And again, Cartesian plane. All students take calculus again. And well, which quadrants have this time the tangent function rather negative? Two and 4, all right? However, is the second quadrant part of the window -π/2 to π/2? We can already just ditch it, all right? What about, okay, yes, the fourth quadrant for sure, all right? And well, so we are looking for the quotient of two numbers that result into -1. Well, there's infinitely many ways to obtain a -1. -2/2, that equals to 1. -5/5, that equals to 1. -5,000 over 5,000, that's -1 also. However, how about tangent y equals to -√2/2, √2/2, because in this case we're looking for common points on the unit circle, and well, we're looking for the points where the y value is equal to the x value. Maybe they vary by the sign, and well, this point actually positive √2/2, comma -√2/2. Okay, and well, what angle would that be? Well, there's a couple of ways to express this angle. Maybe 7π/4. However, is 7π/4 within the window -π/2 to π/2? So maybe we need to rephrase this angle. How about -π/4? That is correct. All right. So that being said, we got the answer. This means arctan -1 equals to -π/4. I know we could have done this maybe in 5 minutes, like, oh, just checking the unit circle and checking the value, but again, it's important to see the concept behind the reason why, to basically follow up with the reason why or how we came up with this inverse trigonometric functions. The fact that we're working with functions with restricted domains, but again, later on in practice, we would need to just looking at the unit circle. Okay. Let's see, approximate inverse trigonometric functions on a calculator. Well, so we do this when we are asked to find the inverse tangent of a number that is not a nice number from the values of the unit circle, namely 1 or ±1, 0. What else? plus minus root of 2 over 2, plus minus root of 3 over 2. So those are the common values, right? So inverse tangent of 5.69. Cosine inverse of negative 3 over 8. Arc sine of negative 0.6. Well, we just use a calculator. And by the way, it's important to understand how to get those values in both radian and degree measures. So let's see. Let's do a couple of those. Let's do at least one. And because we're almost running out of time. So let's do the first one at least. So, okay, let me clear this. So number one, and tangent inverse of 5.69. Okay, so notice we have keys on the graphing calculators. We have keys for sine function, cosine function, and tangent function. However, the inverse trigonometric functions are in blue on the graphing calculator. That means that we need to press the second command. So second tangent, that's to get the inverse tangent function of 5.69. All right, let me close parentheses, and first let me check which mode I'm at. Okay, I'm in radian mode. Let me change to degree mode. We're gonna do the degree first, and that's 80.03. So this is 80.03 degrees, or in radians. I'm gonna go back, click it again, but I'm gonna change the mode to radian mode because we need both actually. And that's going to depend on the context of the problem that we are dealing with. We may need one version or the other, or even both. So that, let me click enter, and that's 1.396, that's 1.40, I guess. Radians. All right.